Thanks for the intro, Sri. Hello, everyone. Good morning, good afternoon. I am Venkatakiran Chanvemalapalli. I work as a principal engineer slash senior solutions architect at Verizon, where I design the scalable enterprise applications powering the generative AI, agentic AI, and other solutions. And in my role, I work with mostly the latest technologies like Google Agent Space, Neural Seek orchestrations framework, IBM AI Orchestrate, and a couple of LLMs that we work as like open source LLMs like Mixtral and Gemini, Gemini Pro, Gemini Flash, and Anthropic. That helps to build enhance our existing systems in multiple domains, in the HR domain, in the corporate domain, in business domain, and consumer domains, and to build the more resilient systems. So today, I'm going to cover reinforcement learning for dynamic LLM data integrations. This is like a scalable path to self-optimizing pipelines. So let me ask you a question here. How many of you are currently working with LLM pipelines in your organizations? Anyone raising hands? That's fine. So then you already know, if you're working in your organization with LLM pipelines, then you already know the pain points today. So I'll walk you through how the reinforcement learning technique can transform these pipelines into self-optimizing systems that deliver not just technical improvements, but business ROIs as well. So the title may sound ambitious, reinforcement learning of dynamic LLMs, but what we will see is that by combining the reinforcement learning techniques, the distributed system designs, and the compliance first engineering, we can transform static pipelines into adaptive self-optimizing systems. Let's begin by setting the stage. So how many of you have seen pipelines break because of some schema changes overnight, or some new data sources added unexpectedly into the pipelines, and we get alerts in the midnight saying like the pipeline has been broken? So all of a sudden we have to wake up and then attend the calls and resolve the issue to make sure the pipelines are processing properly, right? So that's the reality we all face in our jobs. So the main reason for this is enterprise LLMs no longer train on a single curated data set. Instead, they demand high volume, high variety, and high velocity of data sets, ingestion of logs, transactions, click streams, and IoT sensors, and high variety of data structures like structured data, unstructured data, log data, multimodal data, and high velocity updates where the yesterday's data is already stale. So static pipelines that built with the batch ETL tools in the current systems struggle here because they introduce the bottlenecks due to the fixed schema assumptions and manual patchwork to handle the new sources. So escalating the operational costs as the team grows to fight fires. So the worst of all, delayed insights where the models are trained on outdated or inconsistent data. So I like to call that this is the perfect storm of LLM data integration. So, and the cost isn't just technical, it's strategic. If your competitors can integrate fresher, more diverse data, their LLMs become smarter, faster, and more aligned to the business. So this is where the solution we are trying to find out to resolve this kind of issues. So how do we solve this? So by moving from static pipelines to adaptive systems. So the integration of reinforcement learning with large language models is a significant and evolving area of research, particularly for transforming static rule-based data pipelines into dynamic self-optimizing systems with an enterprise context. So this approach aims to address the limitations of a traditional data pipelines, which are often rigid and struggle to adapt changing data sources, schemas, and business needs. So think of a static pipeline like a rigid conveyor belt. So it can only carry what it was designed for. A self-optimizing pipeline, on the other hand, is likely an intelligent logistics system. It detects bottlenecks, reroutes flows, adjusts to demand, and even learns over time. So reinforcement learning gives us exactly that. By embedding reinforcement learning agents into pipelines, we can observe real-time pipeline performance, decide optimal transformations, routing, and resource allocations, act by adapting pipeline behaviors, and learn continuously by maximizing long-term rewards. And importantly, this isn't a rip and replace approach of your current existing pipelines in your organization. So it layers intelligence on top of your existing data infrastructures. Let's go to the next one. So now let's see how the RL is a decision-making framework. Consists of how many layers it consists of, and how this is going to work. Basically, the architecture behind the reinforcement learning. So it consists of 4 interacting layers. Actually, it is 5. I'll talk about the fifth one. So observation layer is the first one that captures the fine-grained telemetry, data quality metrics, schema drifts, pipeline latencies, throughputs, and error patterns. Decision layer, distributed policy networks trained using acrocritic methods. So these policies determine the deduplication, the resource allocation, and the retry strategies. So the action layer will take care of the implementing these adaptations safely by scaling pods in the Kubernetes cluster, rerouting streams in the Kafka or whatever the enterprise is using the streaming system, or adjusting schema validation rules. So the other layer is a feedback layer, which is like a multi-objective reward functions. Evaluate results. Was this throughput is improved, or did we reduce the errors? Did we stay compliant with the organizations? So those kind of actions will be taken care by this feedback layer. So the fifth one that I'm talking about earlier is the role of LLMs in this RL framework. So this is where the dynamic LLM data integrations part of your query comes in. So while reinforcement learning provides the decision-making framework, large language models can be used to supercharge the process by providing context and understanding. So this is a novel and powerful hybrid approach. So intelligent policy advisor. LLMs can be used to provide intelligent guidance to the RL agents. For instance, an LLM can analyze the semantic context of a new data set and suggest a set of relevant data pre-processing steps or transformations. So the policy advisor role helps the RL agents explore more promising search space, preventing it from wasting time on ineffective actions. So LLMs can process and understand unstructured or semi-structured data like natural language text or log files and extract valuable metadata. And this information can then be fed into the pipelines. So the RL agent can then fine-tune the performance of this new integration in real time. So instead of just reacting to the current state, an LLM can forecast further traffic patterns or data changes based on historical and contextual data. By integrating these predictions into reinforcement learning framework, the agent can shift from reactive adaptation to proactive resource scheduling and pipeline adjustments. Because this is essentially a closed loop control system for enterprise data pipelines. And because it's distributed, it scales across very large deployments. Even though we start with small deployments, it can be easily leveraged for the larger deployments in future for an organization. So with this approach, what does this translate to in a practice? So reinforcement learning agents can continuously learn from query execution feedback, dynamic adjusting query plans to balance latency, resolution, resource utilization, and cost in real time. This moves beyond static query optimizers to systems that improve over time. So for machine learning frameworks, this technique can automate the entire lifecycle from data ingestion to model retaining, and it can dynamically select the best data cleaning or feature engineering steps, leading to the better model performance without manual tuning. So RL can be used to create intelligent systems that optimize resource allocations for data processing tasks, ensuring that the compute and storage are used effectively as workloads fluctuate. By making the pipelines adaptive and self-managing, enterprises can handle ever-increasing data volumes and a greater number of diverse data sources without a proportional increase in human efforts. The system learns to scale and manage itself. So in summary, the use of a reinforcement learning technique for dynamic LLM data integration provides a scalable approach for converting static enterprise data pipelines into intelligent self-optimizing systems. So across industries, we have observed 35 to 45% higher throughput because the agents dynamically allocate compute to hotspots and avoid bottlenecks. So 50 to 60% less manual effort since the system handles retries on its own, tuning and error detection autonomously. So we don't have to manually trigger the pipelines upon the changes that has happened on the datasets while the pipeline is in progress. So 6 to 8% of higher LLM accuracy and robustness because improved data quality directly improves the downstream model generalizations. So 280% of ROI within a year and a half, 18 months. That's not just operational savings. Business units report faster product launches, reduced regulatory fines, and improved decision making. This is why reinforcement learning isn't just an academic. It's a driven, measurable enterprise impact. So let's see some of the real world examples, how this is going to transform. So in retail industry, as we all know, integrating the new product catalogs used to take weeks. So with RL driven framework curation, pipelines deduplicate semantically, match attributes dynamically, and now it helps to achieve 10x faster curation speeds. When it comes to healthcare domain, so mapping clinical terminology across hospitals is a very tedious for semantic errors. So with reinforcement learning agents monitoring schema drift and semantic mappings, we can see 70 to 80% of reduction in semantic errors. In the automotive industry for the autonomous vehicles, so pipelines ingest terabytes of sensor data that is coming from LiDARs, radars, and camera streams. And that is where the RL optimizes this fusion across these particular streams, reducing perception errors by 70%. In the cloud operations, so dynamic RL-based resource allocation achieves 55 to 60% of cost savings by minimizing unnecessary data movements and optimizing storage placements. So the takeaway here is this framework adopts a very different industries and compliance regimes. Let's do a technical deep dive on how this RL design works. So we employ a hierarchical topology of agents. So like kind of three types of agents like micro agents, meso agents, and macro agents. So let's see how these agents, what are the functions of these agents and how these agents work together to put this framework. So micro agents works as local optimizers, cleaning records, validating the data integrity, checking schema alignments. And the responsible of these micro agents to take care of these cleaning the records, the data, and everything. Whereas in meso agents operate at the pipeline segment level, deciding how batches flow across clusters. So when it comes to the macro agents, these agents act as a global overseers, allocating compute budgets, setting compliance thresholds, and coordinating between segments. So why this hierarchy? Because enterprise pipelines are too large for a single monolithic agent. So if you have it in a single monolithic agent, it's hard to maintain and it's hard to monitor where the pipeline went wrong. So we believe hierarchical RL balances both local efficiency and the global coherences. When it comes to the technical implementation, these are also equally important. So acrocritic algorithms we're using with parameter sharing for efficiency, and we're using like asynchronous advantage actor critic A3C to enable faster distributed training. So transformer-based policy networks, which excel at handling long-range dependencies like complex schema transformations. So Kubernetes for centralized deployments, because this is a cluster-based deployments, which is much easier to maintain and also much easier to scale. This ensures the portability across cloud, on-prem, and hybrid, all the environments. So distributed event streaming, like event streamers like Kafka or RabbitMQ for a real-time synchronization of agent states. So federated module updates with differential privacy, which allows us to update policies without leaking sensitive enterprise data. So this combination makes the system both scalable and secure. So reward engineering is at the heart of aligning reinforcement learning with business goals. So we define 4 objectives: throughput, quality, efficiency, and compliance. When it comes to throughput, this is measured as data volume processed per unit time. So quality measured as statistical correctness plus semantic accuracy. So efficiency is something like how much useful output we achieve per unit cost. So compliance is adherence to governance policies and regulations in any organization. So the combined reward function is a weighted sum. The trick here is that the dynamic weights. So if an audit is approaching, compliance weight goes up. If latency is critical, throughput weight dominates. So this makes the system adapt to not only to the data, but also to the business context. So training reinforcement learning agents for data pipelines is not trivial. So we solve this in 3 innovations. So pipeline digital twins. So we build high fidelity simulations of production pipelines, same schema, same error nodes. So agents can train safely before going live using this digital twins. Digital twin is nothing but like, when you have a object, so you build a digital version of the same object with the similar configurations that allow you to simulate what is going to happen on a real object. So this is how the digital twins will place a role here. And when it comes to hybrid learning, agents first train offline on historical logs. Once stable, they fine-tune online in shadow mode and where they make decisions, but they don't yet control the live pipelines. And this minimizes the risk. So multiple simulated environments run in parallel, gathering diverse experiences from rare schema drift events to high throughput spikes. So combined, this approach accelerates convergence while protecting production stability. And thanks to oneAPI acceleration, we run this training efficiently across CPUs, GPUs, and other accelerators too. So compliance is often the Achilles heel of adaptive systems. So we build telemetry as compliance first. So privacy preserving observations with a differential privacy ensures individual level data never leaks out of the systems. So automatic redaction of PII and PHI data, which is like sensitive data before logs are stored in the systems. So audit trails for every agent decision. So we can explain why a reroute or transformation was chosen. So on the technical safeguard side, homomorphic encryption is for sensitive metrics and secure multi-party computation for cross-domain insights, and hardware security modules integrated directly into the agent's decisions flow. This makes the system not only adaptive, but also trustworthy, a critical requirement in healthcare, finance, and other regulated industries. So finally, how do we move from theory to practice? So basically, in your enterprise, we recommend a 4-phase approach. Like first we do the assessments, and then we do the pilot of this with the small applications, and scale deployments, and continuous evolutions. So in the assessments phase, what we can do is like we can do the baseline analysis of the pipelines, identify the pain points in the existing pipelines and what the business goals are. So how to transform these static pipelines into dynamic pipelines by using this framework. So that's the assessment phase. And when it comes to pilot phase, which is going to take like 8 to 12 weeks, so deploy the reinforcement learning agents in shadow mode, train on logs, validate against the KPIs, whether we are getting good results or whether the agents are getting hallucinated with the log data, and so on and so forth. And once the RL agents looks good and they are past the pilot testing, so then we can scale the deployments. So expand the coverage and implement the hierarchical coordination, integrate with monitoring dashboards that helps you to scale these deployments. So continuous evolution is something like automated updates, curriculum learning for agents, and contributing improvements back to open standards. So we are also releasing an open source starter kit and guide, which makes it easier for begin experimenting. In conclusion, enterprise LLMs pipelines are hitting scalability and cost ceilings, whereas in reinforcement learning provides a scalable, intelligent way forward, delivering measurable throughput, efficiency, and ROI improvements. So by layering reinforcement learning intelligence over existing infrastructure and by embedding compliance-first telemetry, we can build pipelines that are not just faster and cheaper, but also self-optimizing, adaptive, and trustworthy.